Welcome to class meeting 26 of EECE574, the graduate level probability and random processes. We have the announcement about the final exam, and it will be taken on Wednesday, June 7th. It's Wednesday, okay? It's not Tuesday, Thursday. It's Wednesday, not here in LG 102, but the next room, 104. It seems that somebody already reserved this classroom for the Wednesday night. And also, since the final exam date is now fixed, your topics for the voluntary project must be discussed before this day and must be submitted by, where it is, June 15th. June 16th, the Friday, is the final date for me to upload your grade. So the voluntary project must be submitted one day earlier. Got it? Lecture notes, videos are available. It seems I'm kind of lying again and again, saying that the homeworks will be assigned but not assigned. I will, okay? Here goes our overview. We just finished the stochastic convergence and limit theorems. And we are going to enter into the topic of systems with stochastic inputs. Because we are mostly electrical engineers, we view physical electrical system by abstractizing it using a mathematical system, that is a mapping rule. So here is a function. You can view it as a box that has input and output. And in your undergraduate program, you usually learned the case where your input is a deterministic signal. But here, we also have to consider, as a graduate level researcher and engineer, we have to consider the input with uncertainty. In that case, what would be the output? In order to understand that, first, we need the topic of stochastic calculus, as stated here. So today we focus on this problem. By the way, let's review what we learned last time. First, we reviewed kind of what is the limit point of a sequence of real numbers. And now you have some idea, right? Some visualizing method. So you draw a kind of graph of a sequence. So this is n axis, 1, 2, 3, 4, up to infinity. And here is, for example, if sequence is a real valued sequence, you have now dots, right? You can use, of course, stem function in the MATLAB, but suppose you use the dots. Then what is a limit point of a sequence? So suppose you claim a constant c is a limit point, which means that you find value c in the vertical axis, and then you take whatever epsilon positive, and you draw a band that has width 2 epsilon. Then what? In this band, you must be able to find countably infinite number of n values. Then it's a limit point. So I gave you an example of a sequence xn, that is sine n. Interestingly, sine n, where n is an integer, a natural number, has every real number between 1 and -1 as a limit point. For example, suppose you choose 1 over square root pi. Then is it a limit point of that sequence? Yes. Because if you find that value, 1 over pi, square root pi in the y-axis, vertical axis, and you set a band, then your sine n graph have countably infinite integer n's where your value falls in that band, something like that. And given that, we next studied two strange definitions called lim sup and lim inf of a sequence of real numbers. By the way, there is one correction. So last time I wrote in this way, lim sup xn and n to infinity. Actually, this is wrong because lim sup is not the sup of xn. Okay, lim sup is one concept. So I had to write like this. Okay, so instead of writing lim, you put lim sup. Similarly, you have to write in this way, lim inf xn. This is a kind of new notation that is different from limit. Got it? So here goes the lim sup and lim inf over sequence xn. And I emphasize that that is not the supremum of the limit points over sequence. Lim inf is not the infimum of the limit points over sequence. It's a different concept. What you do is that you construct a monotonically decreasing sequence and define the limit of it, which is finite or either negative infinity, as the lim sup. And you define an increasing sequence and define the limit of that as what? As a lim inf. So lim sup, if it exists and finite, is always greater than or equal to lim inf. And interestingly, if the sequence has the limit, the unique limit, then lim sup and lim inf are the same. So without using that magic spell for every epsilon positive blah, 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 to define your limit over sequence, you can just use lim sup and lim inf instead. And then say that, okay, this number limit over sequence equals lim sup equals lim inf, in case the sequence has the limit. Got it? Similarly, given a sequence of subsets, in our case, probably the subsets would be used to represent events in some probabilistic experiment. So suppose we have a sequence of events, then we can similarly define lim sup and lim inf of a sequence of events. Then suddenly we can kind of bypass defining the limit of events from the beginning, but first defining the lim sup and lim inf of a sequence of events, and then claim a sequence of events converges if the lim sup of the event sequence and lim inf of the event sequence are identical. Something like that. Got it? So we can define the lim sup and lim inf of a sequence of events. Then here goes our goal. There is actually a set of theorems. The first Borel-Cantalli lemma, second Borel-Cantalli lemma. But anyway, the most important use of it is that you show some probability of event equals 1. So this is useful in showing almost sure convergence. Of course, the Borel-Cantalli lemma is not used always to prove the convergence almost sure. However, almost sure convergence, if you want to prove that, if the proof is not trivial, in many cases, you rely on the Borel-Cantalli lemma. And here goes some lim sup of event n. So in order to prove some sequence of events converges, probability of, in order to show some limit when measured using the probability measure equals 1 with the probability 1, that is related to the almost sure convergence, you need the notion of lim sup of events. And also, you can also show that some lim inf, something like that, to prove your result. Let's review what we wrote here. Okay, so where it is. Okay, it seems I flipped it. Okay, so here, let me flip. Something like this. Okay. Anyway, so we need the idea of a sequence of events to prove almost sure convergence. Next one was on the Monte Carlo integration. So given a situation where you need to compute the integral of some function, what you do is that you introduce a random variable and solve the problem by relying on the law of large numbers. So what you do is that given some problem like this, you view it as the expectation of g of x, where random variable x is uniform. Okay, so this is equals to 1 on x 0, 1. So you can strangely convert an integral form into expectation, and then what? You use the law of large numbers to approximate. And by the way, this method has very long history, and probably you've heard so-called Biffon's needle, where this guy, probably French, was some officer in the 19th century European war field, and he was captured by the enemy. And since he was an officer, he was kind of not tortured, but just put in some tent, and he had nothing to do. So he just drew some lines on the ground and started to throw a needle and counted the number of throw and number of the events where your needle touches one of the lines. Of course, the needle is shorter than this space. Suppose they are squares. And he showed kind of using a law of large numbers that some probability of that event can be replaced by simple what? Law of large numbers. That is what? That is same as what? The number of 0, 1 random variable realizing to 1, right? So that is a very interesting problem. You can also compute the value of pi by doing this. For example, suppose you have some pen that is kind of square shaped. And then what you do is that you draw a circle, and then you throw a coin and check whether your coin rests in this area or in that area. By defining a 0, 1 random variable, and then calculating the arithmetic average of ones, then you can approximate the value of pi. Of course, the convergence is very, very slow. But anyway, there are many ways to convert non-probabilistic problem to probabilistic problem, and then use, for example, law of large numbers or some convergence theorem to prove that. And this is a widely used technique. And when I read Terence Tao's some very short book related to how to prove, I found that given any problem, he converted it to a kind of major theoretic problem, which means that the problem may be converted to a probability-related problem and then solve. That is very interesting approach. Anyway, so we also have seen Monte Carlo integration. And finally, we summarize 4 modes of convergence of a sequence of random variables. Today's topic is stochastic calculus, especially mean square calculus. However, before we talk about mean square calculus, let's see what we need. Continuity, differentiation, and integration. These are topics of calculus, right? Integration, differentiation. Before talking about that, we learned the notion of continuity over function. Do you remember? In high school, here goes the definition. Suppose x is just the real valued function defined on the entire real line for simplicity. The function x is continuous at t0. What does that mean? What does this mean? If the limit of xt when t tends to t0 equals, anybody? Yeah, that is high school level. As I told you, you must write this way. And this looks very strange, but contains a lot of information you remember. So definitely, what is the limit of t when t tends to infinity? Of course, that is t0. So it reduces to your high school version of the continuity over function at t0. However, no longer you remember that way. You remember this new way. And what does this mean? This limiting operation can pass through that parenthesis. Actually, that is not a mathematical term, but when we just view, it kind of passes through this parenthesis, and here you go. If this holds at t0, then x is continuous at t0. What if this above thing holds for all t0? Then x is continuous if x is continuous for all t. Got it? So there are 2 notions of continuity. Continuous at a point. And then you just extend that idea for every t, usually in the domain. But if you extend that for every t, then the function is continuous at every real number x, number t. Got it? Of course, you can restrict the domain to an interval and talk about continuity. Got it? The problem is that we haven't defined what does this mean in our high school. Anybody? Anybody remember what is the definition of this by deleting all the information you learned after entering the college? Actually, there is no definition. That's the problem of Korean high school math. Now, what is this one? So here goes the definition. Given x, just for simplicity, I will just use domain and range or R, okay? Given x, a function, limit x of t, we say equals c if. So anybody? Yes, we must start with for every epsilon positive. Okay, for every epsilon positive. Now, by the way, what do we want to do by this way? As an engineer, forget about limit. Always remember it as an approximation. What you do is that you want to approximate x of t by some value c for sufficiently close t to t0. Got it? So let me repeat. This is so important. This must be interpreted as x of t is well approximated by c for sufficiently close t to t0. Got it? So again and again, this for every epsilon positive spell and for sufficiently something appears again and again and again and again in our analysis, introductory analysis. So we want to mathematically precisely define this notion by stating something here. What do we do? There exists delta of epsilon. So the value delta is chosen after you choose epsilon. And this is positive such that, t minus t0 less than delta of epsilon implies, because we want to eventually claim that x of t is close to c. So x of t minus c is less than epsilon. Okay. So for every epsilon positive, the error is less than epsilon. Got it? By the way, as far as we choose epsilon as a positive value, I said that the equality inclusion doesn't that matter in considering the limit of a sequence, right? And that is almost the same. Okay. Here, you must be careful in that t is not necessarily t0. Okay. So if you put equality here, and then you have some problem, because for every epsilon positive, if t0 is in the domain, right? By choosing what? By choosing delta as 0 and delta of epsilon as 0, if there is equality, then you only choose t equals t0. And this is always true if it is continuous. So it's you'd better just remove all the equalities there. Got it? For simplicity. Yeah. Forget about equality. It doesn't that matter as far as there is no equality here. Got it? Okay. Anyway, so this is the definition of the limit of x of t when t tends to t0. Question. Given a function x and given some t0, this limit always exists or not? And you already know, right? You already know from the example of your high school math. Suppose x of t equals 1 over t. Of course, t equals 0. 0 is not in the domain. But even though 0 is not in the domain, you still consider this, right? And what about that limit? It does not exist, right? However, interesting thing is that whenever you have some limit, whether it is a limit of the sequence of real numbers, if you have a limit of a function at some point, as far as the limit exists, it's unique, okay? Because we deal with real value or complex value here. If you extend that to function, then you sometimes have to introduce the notion of equivalence class, right? So even though they may be different, but you under certain condition regard them the same, something like that. Okay, so anyway, so we need the definition of the limit of a function when t tends to some t0. And then by using this idea, we define the continuity. Got it? And for this example, we have something like this. This is also from our high school math. And as you see, t equals 1. 1 is not in the domain of this function, right? Because we can never divide something by 0. But we can still define the limit, right? What is this? That is 2, as you learned in high school math. The problem is that since the domain excludes 1, in this case, what? The function is not continuous at 1. But that is kind of obvious because 1 is not in the domain. Anyway, you cannot define the right-hand side, so it cannot be continuous at that point. However, there are many cases where the function is not continuous, and the simplest one can be something like this. You have y equals x except x of t equals t except that t equals 0, which is defined as 1. Then what happens? For sufficiently close t to 0, the function value is 0. However, that is different from the function evaluated at 1, something like that. So that is the notion of continuity. What about the differentiation or first order derivative of a function? And what is the integration? They all involve some kind of limit process. But we first will see the stochastic continuity first. So here goes the question. First, let's refresh our memory. Given a random process x, capital X, continuous time random process, the first question is, what is x of t0? What was that? Anybody? A random variable, right? So this is a random variable. Second question is this. What is then the limit of random process x of t when t tends to infinity? Of course, you can say that it may exist or not, right? Right? Now, what if it exists? What if that limit exists? What is that? And your answer must be a random variable. Why? Because we introduced many different notations. This is one of the notation for continuous time random process, right? Sometimes I used capital X of ST. So if you want, I may write this way, okay? So here is a kind of random outcome generator. And here goes your small s. And here is a mapping rule. Depending on the input value s, a guy is here and select so-called a sample path and provides it to you, right? And we call that output as a random process. Now we fix t to t0. Then what do we have? A random variable, right? So this one, if exists, must be a random variable. Then here goes the definition. If the limit of x of t when t tends to t0 equals x of t0. This is not obvious, right? As I told you, as we've seen in a deterministic signal, the left-hand side, the limit of a function when t tends to t0 is not necessarily equal to the function evaluated at t0. Similarly, this limit is not necessarily equal to this one, a random variable, right? Then, what do we mean by this one? That is different from the continuity of a deterministic function at t equals t0, because now you involve what? Not a function, but a random process. So what does this mean? So let's see by using that. And here, this can be replaced as limit x of t of s, t tends to t0, equals s t0 of s. Now, we can clearly see that, okay, what is right-hand side? That is a function of s. What is the left-hand side? If it exists, that must be a function of s. And we know from our notion, function equals some function has already many definitions. Everywhere equality, right? If you have two functions, and also almost everywhere equality, am I right? But however, here on the left-hand side, you don't have just a single function. You have how many? Uncountably infinite number of functions, because the path t tends to t0 is not unique. There are uncountably many ways to approach t0 on this one-dimensional t line. You may approach this way, right? You may approach this way. You may approach that way. You may approach other ways, right? Many, many ways. What does that mean? Here on the left-hand side, you have uncountably infinite ways to choose your kind of sequence of functions. But one good thing is this. If this exists, then what? You can choose any sequence of t that converges to t0, not necessarily equal to t0. And you can construct a sequence. Now you have what? Countably infinite number of random variables that converges to another random variable or not, right? So the problem suddenly is equivalent to what? Convergence of a sequence of random variables to another random variable, which was the topic of previous lectures. The convergence of a sequence of random variables. Nothing but that topic. And you know, this equality or this convergence has 4 modes of convergence. Right? Almost sure convergence in the p mean, in probability, and in distribution. So what does this mean? Again, you have to specify. Sometimes you may say that, okay, I have continuity of a random process at t0 in almost sure sense, or in the mean square sense, or in probability, or in distribution, right? So when we talk about just simply continuity, not even differentiation and integration, when we just talk about continuity of a random process at some specific point, we need a knowledge of the convergence of sequences of random variables. And we have to choose which one, the strongest or the weakest. By the way, when we talk about strong law, large, and weak law, actually we talk about almost sure convergence and improbability, right? Convergence, but anyway, so which one? And of course, we can never cover every convergence issue in this course and in any course. And most of the engineering courses talk about what? This one, especially P not only greater than or equal to 1, but 2. And that is called, that stochastic calculus is called the mean square calculus. So when you talk about the convergence of a sequence of random variables, we use that to show continuity or derivative or integration of a random process. We love to use convergence in the second mean. Why? Why? Anybody? Why? Because we really love mean squared error metric, right? We love mean squared error metric. That's why we love mean square convergence and mean square calculus, stochastic calculus. However, that is not the only stochastic calculus. That's what you have to remember. But in many cases, we really love mean squared error as our performance metric. And most of the times, mean square calculus is enough. For example, suppose you want to show some probability of the random process evaluated at t0 greater than or equal to some value. So suppose you want to find something like this. So given a random process X, you want to find the probability of event that X of t0 less than X. That is simply CDF or first order CDF of random process X at t0, right? However, in some cases, this cannot be obtained directly. So what you do is what? You consider this as what? You want to approximate like this. Okay, what about this? And you want to make some statement like this. Okay, sorry. Okay. So probably as an engineer, what I do is that just something like this for sufficiently small epsilon, something like that. And what? This requires only the CDF, right? Because you want to compute the probability. So you don't need, in some cases, not exactly in this case, you don't need mean square calculus, but you need some kind of in distribution stochastic calculus, but you don't need that because if you can prove that one, this is an immediate consequence. In many cases, I'm not saying that you can do every time because we need a lot of subtleties. But anyway, so mean square calculus is very powerful. That's what I want to say. Because sometimes you just need this convergence or that convergence. But as we know, as far as you can prove mean square convergence, these two are just guaranteed. Got it? So let's see. Then here goes a new notation. It's like L dot I dot M dot and X of t. And here T2 T0 equals X of T0. This is a new notation. So this is a new notation, and this is kind of new equality we want to define. What does this mean? This is different from limit. We want to say something different. By what? Actually, this equality means this equality in the mean square sense. Got it? So we don't write like this and where equality is in the mean square sense. We just write in this way. And this means mean square continuity. So X of t is mean square continuous at t0 is this. Got it? And as you know from the definition of mean square convergence, so let's define this notation like this. Here goes the definition. Okay. Limit in the mean of x of t as t tends to t0 equals x of t0 means this one. So precisely speaking, you have to write this way. Expectation of x of t0 plus epsilon minus x of t0 mean squared error tends to 0 as epsilon tends to 0. So this is what? This is the definition of x mean square continuous at t0. What about this? If this holds for all t, then the random process is continuous for all t in the mean square sense. Ready? So now you understand why I spent so much time to kind of introduce or motivate the convergence of a sequence of random variables, right? And you suddenly see that even though there is no sequence, by constructing a sequence epsilon sub n that converges to 0, this problem reduces to the convergence of a sequence of random variables to another random variable if you specify t, right? So this is the definition of mean square continuity. Let me repeat. This one is the definition of mean square continuity at t0. And this is, if I put for all t, the definition of the mean square continuity for all t. And here goes a theorem that is interesting. So given a random process x of t, this is mean square continuous at, for example, every t. And this theorem says that if and only if, which means that it's equivalent, that the autocorrelation function, so we assume that the process is regular or second order, which means that the power is finite. The autocorrelation function is continuous at the point t1 equals t2 equals t. What does this mean? By the way, what is this one? You still remember? Defined as x of t1, x of t2, and if you want to put conjugate, then you put conjugate on the right side. That is the convention. If x is real valued process, you don't need this one, right? And definitely, this function is a two-variable function because you can choose different t1 and t2, right? And at each t1, t2 pair, you have some number. That is the function has two-dimensional domain. Now, what does it say? You draw a line, t1 equals t2, and at every point on this line, the function, the autocorrelation function is continuous. So you may have some discontinuity here, but for every t at t1 equals t2 equals t, you have continuity. So now let's see, right? See that? This is a random process. Single parameter. Actually, it's two parameter, right? Because x has t and s. But anyway, it's mean square continuous. And this is a deterministic function, right? Autocorrelation function is a deterministic function. So this theorem allows you to replace stochastic continuity in the mean square sense to what? Non-stochastic continuity of autocorrelation function. And probably some of you wondered why this course and almost every random process courses talk about autocorrelation function, cross-correlation function, covariance function repeatedly, because of this one, okay? And also, as I told you, in statistical inference, when you especially make estimation, you usually use mean square error minimization. That's why mean square calculus is important, and what? Autocorrelation function is important. Ready? So let's see. So we start from what? The definition, mean square continuous, right? What does that mean? This error, right? As epsilon tends to 0, goes to 0, right? Or for sufficiently small epsilon, this mean square error is also small. Now let's see by expanding that one. So first you have 4 terms, and first term is what? This one. Second term is that one. Third term and last term. Now, let's take epsilon tends to 0, and you want to show this tends to 0. So epsilon tends to 0, then epsilon, epsilon. So here, suppose this is t, you have t comma t, and you have t plus epsilon comma t plus epsilon, and what? T comma t plus epsilon, this point, and that point is t plus epsilon comma t, right? Now you let epsilon tends to 0. What does that mean? Your t comma t is fixed, but all the 3 points kind of converges to that point. Now what happens? As we know from our calculus, what happens? If the two-dimensional function is continuous at t comma t, right? Whatever path you choose to that t comma t, they must have the same value. You know that, right? So if autocorrelation is continuous at t comma t, then this tends to 0. Right? Of course, the converse is a little bit hard to prove, but usually we use proof by contradiction or contraposition if you choose a little bit differently, so we can prove that. Got it? So the idea is this one, okay? Mean square continuity written using expectation just can be visualized this figure with 4 points. And as epsilon tends to infinity, your that's h 4 points converges to t comma t, and from your knowledge of undergraduate calculus, if function is continuous at this point, all the terms have the same value. So you have that canceled by that one, and this canceled by that one. So it tends to 0, something like that. Got it? Okay. And here goes a simple result or obvious consequence of this theorem. Suppose you have a Y-sense stationary random process that is mean square continuous. What does that mean? By the way, when you draw a graph over an autocorrelation function over Y-sense stationary random process, what happens? Along this line, the value is what? Constant, right? Of course, that value, the value on that line and the value on this line may differ. But it can be represented by a single number. And also, we can introduce a new parameter tau, that is the time difference between T1 and T2. We usually subtract T2 from T1, and we can construct a new function. Then what happens? The new function, single variable function, gives us this as what? XX. You subtract that, 0. And this becomes negative R XX, negative epsilon, R XX, positive epsilon, R XX 0. So you have if and only if R sub XX of tau is continuous at t equals 0, because here if you set epsilon tends to 0, then you talk about the continuity of the single variable autocorrelation function is continuous at 0, right? Okay, now here goes a more difficult idea of the mean square derivative over random process. So in order to understand this one, let's simplify and review our prior knowledge. So given a continuous time signal, okay? Of course, in your high school math and calculus, it was a function. It was not a time function, but as an electrical engineer, we love x of t rather than f of x. So given a continuous time signal, x of t. What do we mean by x dot t, which is the notation by Isaac Newton? What is d dt of x of t? The notation by Leibniz. So what is that? What is the definition? To talk about that, similar to the definitions of continuity, we first defined what? Continuity at some point and continuous function. Similarly, we talk about kind of x dot at some t0 and x dot of t, because this is a value and this is a function of t. Got it? So we have a similar pattern again and again. So let me ask you, given a function x of t and you choose some t0, what do you mean by x dot of t0 or dx dt at t equals t0? And you have some very qualitative definition from your high school. What was that? You started from the slope, right? So this is t and this is x. And suppose you have a smooth enough function of t and you choose t0. And here is t0 comma x of t0. And what do? You consider some displacement delta according to your high school textbook. So here goes interval of length delta. And what do? Here, you have t0 plus delta comma x of t0 plus delta. And here, you compute the slope of the straight line that connecting these 2 points. And what? Define x of t0 plus delta minus x of t0 divided by t0 plus delta minus t0. Okay, right? And as far as delta is not 0, okay, this is well defined. And also, all the points in the interval, all the points at the end points are well defined. Now, what do? You take the limit of this quantity as delta tends to 0. Let me use epsilon. Let me use epsilon. Epsilon would be better because we just use the epsilon. So epsilon tends to 0. Yeah, something like that. So epsilon, 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 epsilon. Got it? So again, this can be viewed as a function of t, and you have, of course, it's a function of epsilon, and you consider the limit of this function of epsilon when epsilon tends to 0. So it's a kind of limit over function. However, if the limit exists, then what? You can construct any sequence of epsilon that converges to 0, and you must have the same limit, right? So we can kind of convert that as a what? Limit over sequence of real numbers, whether it converges or not. So if that converges for all choice of sequence of epsilon converging to 0, and if they are the same, what? We can say that, okay, that is some specific number, right? And we may say that, okay, if this exists, then let's use this notation, x dot of t0, okay? So this is our definition vague of x dot evaluated at t0. However, this is not good. So what do we do? Again, we may use that spec for every epsilon positive, blah, 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 blah. But it's not that difficult because this is kind of function of epsilon. And we've already defined the limit of a function when the argument tends to some finite value. We've already done that by using epsilon and delta method, right? So that is enough by the definition, for the definition. So we define x dot of t0 for some specific t0. Now, suppose that can be obtained for all t. Then what do we say? The function is differentiable. Not just t0, for all t, right? So similar to continuity, we have differentiation of x at t0 and derivative of x of t. That as a function of t, right? So right? In Korean, 도함수, right? 일개 도함수, the first order derivative of x of t. Now, let's do something similar for a random process. Okay? So, first thing we want to do is what? Probably we want to define something similar to this one, right? And then we extend that notion to something similar to that one, x dot of t. So, yeah, here goes the definition. So let's consider some stochastic limit. So this is a what? This is a random variable given t0 and epsilon. This is another random variable, right? Now, by changing epsilon, you have what? You have many random variables parameterized by epsilon. Now, you consider epsilon tends to 0. And as I told you, you may construct a lot of different sequences of epsilons that converge to 0. So it becomes what? Limit of a sequence of random variables in your concept, right? Now, this may exist or not, right? Similar to a sequence of functions. Suppose your function is what? X to the n. Now, n tends to infinity. Does that sequence of function converges? No, right? You know, right? Similarly, that limit may exist or not. But suppose if it exists, then, of course, we assume some uniqueness on the some other definition of equivalence class. But if that exists, we are going to say that this is what? X dot of t0. But this is somehow what? In some sense, or more sure sense, or in probability sense, or in distribution sense, or in some piece mean. But what do we do in the mean square calculus? That equality would be limit in the mean. So what we do is that in stochastic calculus, sorry. So this is what? Mean square derivative of x at t0, something like that. Got it? And this is, again, a notation. What would be the definition using expectation? Simple. You subtract this one, that is a random variable, from this random variable. And what? We take the absolute value square and take the expectation, and what? That tends to 0 as epsilon tends to 0. Now, we have defined the mean square derivative of x at t0. What about just the first order derivative of x of t? That is now this one. So suppose what? X prime. Okay. It seems here I use prime, not dot. Okay. X prime. Yeah. So here, if this holds for all epsilon, and of course for all t, sorry, not for all epsilon, for all t, then this new random process called the derivative of the random process of x. So it's like by using the stochastic calculus, right, you can somehow link two random processes, x of t and some other one. But that is now called what? The first derivative of the random process x in the mean square sense. Got it? Now, similar to the previous continuity, we can show that x of t with autocorrelation function Rxx has a mean square derivative if and only if the partial derivative with respect to t1 and t2 exists at t1 equals t2 equals t. So again, it's like here you have a two-dimensional function and consider this line of t1 equals t2. And this theorem says that your random process with autocorrelation function has a mean square derivative. What? If this function of autocorrelation function is differentiable at that t comma t. Got it? And also, you have some other results. Okay, just a second. Yeah. This theorem, if the random process now has mean path mu sub x of t and the autocorrelation function, and this x of t is has mean square derivative. So given that, interesting thing is that your derivative of the mean path is given by the derivative, as the mean of the derivative. What does this mean? So left-hand side is the expectation of x prime of t. What about the right-hand side? Right-hand side is the derivative of expectation of x of t. What does this mean in our ordinary language, not mathematical term? You can interchange the order of expectation of derivative. It sounds something similar to the consequence of uniform convergence. As I told you, when you have a sequence of functions, and if the sequence of functions converges to another function uniformly, then there are many good things happens. Especially, you can change the order of summation of your order of integration and the limit the summation and limit, something like that, derivative. Similar thing again happens. So under this condition, you can find you can find the expectation of derivative by computing the derivative of the expectation under this condition. So existence of the mean square derivative is very, very useful. In many engineering problems, we just assume that any order of the limit operations results in the same result. That is not true, right? As I told you already, given this sequence of m and n, if you change the order, you have the different result, right? Am I right? So changing the order of two limiting operations. Expectation is also a limiting operation because it involves integration anyway, right? And derivative, of course, requires some limiting operation. And we have a good result. And also, see this. What is this one? Autocorrelation of the derivative process, mean square derivative process, can be obtained by differentiating the original random process's autocorrelation function. This is very, very interesting, right? And also, we can kind of have a corollary to this theorem by putting one more condition of y-sense stationarity. And in that case, we have that single variable autocorrelation function that has better property. Now, integration. Again, let's consider a simpler one. What is the derivative of a deterministic signal x of t on the interval t1, t2? What is the definition? Here goes the difficulty of this course, because most of you only know the Riemann integration, or even some of you do not know the name of Riemann integration. The problem is that we usually need Lebesgue integration for the analysis because it makes more sense. And if Lebesgue integration exists given an integral, then it's the same as Riemann integration. However, some case Riemann integration does not exist, but Lebesgue integration exists. And let me give you an example. Okay. Suppose you have a function x of t that is defined on this interval 0, 1, and x of t equals 1 for all t in, okay. Something like this. So you have, Q. So you have the set of rational numbers and you intersect, which means that for every rational number of t, you have zeros. So definitely here you have 0, here you have 0, 1/2, you have 0, 1/4, 3/4, zeros, something like that. But for example, 1 over pi, you have 1. 1 over square root 2, you have 1. Got it? Now, what is your integral in the Riemann sense? What was the definition of Riemann integral? One unfortunate thing in our South Korea high school math is that we never define the integration in our high school math, the Riemann integration properly. What is the definition? Now, from your undergraduate calculus, what is the Riemann integral of this function x of t on this interval when x of t is given like that? And what they do is that we divide that integration interval into what? Into non-overlapping intervals by considering some so-called partitions. So we introduce some points, right? So here we have T0 equals 0, T1, T2, dot, 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 T sub n equals 1. So let me see, not this one. This is not good. Okay, let me put some script like this. Maybe wrong. Yeah, anyway. So first you divide the interval into n subintervals. And when you refine this partitioning, what you do is that you still keep the previous points, but include some other points. Got it? And what is also important is that as you increase the parameter n to infinity, what you must have is that the largest, the length of the biggest interval must tend to 0. Okay? That is the condition. And now what you do is that you define the so-called upper Riemann integral and lower Riemann integral. So it's like you define lim sup and lim imp. So what you do is that you define something like this. And you define something like that. And we check whether they are the same. This is called the upper Riemann integral, and that is called lower Riemann integral. And if they are the same, we say that the Riemann integral exists and is that value. But what about this one? What is the definition of that one? That is defined as n tends to infinity. And as I told you, we already introduced some sequence of partitions, right? And the bigger partition must include that points on the previous partition, right? And what we do is that we now sum up the value of value from each interval. There are n intervals in the nth stage, right? And what we do is that here we choose max, okay, of x of t on the ith interval. Something like this. So what we do is that given that interval, right, we calculate the length of that interval and we find the maximum value of function on this interval and multiply. So biggest square we have here. By the way, since this is all non-negative, this definition works well. First, usually we define the Riemann integral for non-negative function. And fortunately, that was a non-negative function, something like this. And the left-hand side is similarly defined. Something like this. So we involve two limits to define the Riemann integral. And as I told you, in our high school math, there is no definition of limit. And how can we precisely define Riemann integral? That was our unfortunate curriculum. But anyway, so Riemann integral exists if the upper Riemann integral and lower Riemann integral both exist and are the same. Now, let's see what is the upper Riemann integral for this integration. So you partition the interval and take the maximum value. What is that? That is always 1, because in any interval, you can find an irrational number that has value 1. Now, what is the minimum? For any interval, you can find the rational number. That is called the denseness of rational number, right? So you can find what? The lower Riemann integral 0 for this function. The upper Riemann integral 1 for this function. Now they are different. What can you say? The Riemann integral does not exist. The problem is that we don't want that. As we already know, suppose we find the length of this subset of the domain by using our notion of measure. What is the length? 0. What is the length of this one? 1. So we want to say as an engineer, okay, this function is, I learned some interesting idea in Professor Zhou's class. Okay, right. This function is almost everywhere equal to a constant function. And that constant function, almost everywhere equal constant function, has Riemann integral 1. So as an engineer, we want to say that integral is 1. That is why we need a different definition of integral than from the Riemann integral. And one of the integration invented is called the Lebesgue integral. Invented by Lebesgue. And that involves the notion of measure. And the core of the measure theory is the Lebesgue integration. That's the difficulty. Got it? So when I was a graduate student, not Purdue University, I was a graduate student of Purdue University, but there was a neighboring other university, the Michigan University, University of Michigan. And we heard some rumor like this. Hey, we heard that the University of Michigan has the electrical and computer engineering department that offers 4 probability courses, not math courses, 4 electrical engineering probability courses for electrical engineering graduate students. And I wondered why at that time. And suddenly, after 2 years, I got to know, because in my case, my professor asked me to take 4 analysis, measure theory, measure theoretic probability courses at the Department of Math, right? So very similar. So we need a lot of analysis related knowledge to kind of work properly as a graduate student in communications engineering, because you need the notion of convergence of a sequence of random variables first, and then you need to know some knowledge on the stochastic calculus. And that involves a lot of knowledge, measure theory, measure theoretic probability theory, and something like that. So that's the difficulty. And that was the goal, actually, of this course of this year. And we will continue next time on this mean square integral. Okay, let me stop.